Rigid body dynamics helps us analyze the motion of mechanisms made of rigid components. Hello, I'm Armin. Welcome to my channel. In this video, I'll show you how to model a two-cylinder engine and connect its components using revolute, general, and cylindrical joints. We'll also apply an actuator to drive the crankshaft and observe the engine's motion. Before we begin, let's take a quick look at the model. Rigid dynamics is a tool for analyzing the motion of a mechanism when deformation is not important. In other words, stiffness is ignored in the equations of motion, so the geometry does not require a volume mesh, and we focus only on the movement of the mechanism. A rigid body has 6 degrees of freedom, and this method uses the explicit dynamics solver, allowing us to simulate models over long durations efficiently. Rigid dynamics are widely used across many industries, but in this tutorial, I'll demonstrate it using a two-cylinder engine to investigate the mechanism's motion. All components are connected through joints, which can be adjusted for any of the 6 degrees of freedom. A revolute joint allows rotation around a single axis, while a cylindrical joint allows translation along and rotation around the z-axis. We can also use a general joint to fix or free each of the 6 degrees of freedom as needed. Note that, unlike contact definitions, joints do not require any surface mesh. We'll model a two-cylinder engine using the rigid dynamics system. Before running the analysis, I'll prepare the geometry in SpaceClaim. Since the geometry is rigid, there's no need to assign material properties except when we include gravity effects. For this engine, I'll define 7 joints, including revolute, cylindrical, and general joints, as shown in the figure. I'll also add a joint load to act as an actuator, applying a rotational velocity to drive the crankshaft. Finally, we'll run the simulation and observe the mechanism's motion. After solving, we'll observe the mechanism's motion under 2 conditions. In the first case, it accelerates from 0 to 1000 RPM within 1 second. In the second case, it accelerates from 0 to 1000 RPM in 1 second, runs at a constant speed for 2 seconds, and then decelerates over 3 seconds. That's enough explanation. Let's start the modeling. We want to analyze a rigid mechanism, so we need to add a rigid dynamics system. I'll double-click on Rigid Dynamics in the Analysis system. In this type of analysis, we don't need to define any material properties because all the components are considered rigid bodies. Let's move on to the geometry. I'll right-click on Geometry, go to Import Geometry, and click Browse. Then I'll select the assembly file and click Open. Now let's edit the geometry in SpaceClaim. I'll right-click on Geometry and select Edit Geometry in SpaceClaim. The geometry is being imported. This may take a few moments. The two-cylinder engine with the crankshaft has been successfully imported, and we're ready to analyze it. We don't need the 2 cylinder covers, so I'll select Cover 1 and Cover 2, right-click, choose Suppress from Physics, and hide them. There you go. These are the components we need for the analysis. Before we start modeling, it's important to check for possible geometry issues. I'll navigate to the Prepare tab and click on Interference. There are no interferences between the components. Next, I'll go to the Repair tab and click on Extra Edges. Fortunately, there are no geometry errors detected. Now I'll press Escape and zoom in. As you can see, there's a small gap between the connecting rod bearing and the crankshaft. We need to fill this gap. I'll click on the bearing of the connecting rod, go to the Design tab, and select the push operator. I'll enable the No Merge option, set the target to Up to, and click on the crankshaft journal. As you can see, the gap is now filled. Let's repeat the same process for the other connecting rod. Select the bearing, choose Up to, and click on the crankshaft. Now the bearing diameter of the connecting rod matches the crankshaft. Let's also check the bush bearings. As you can see, there's a small gap, and we need to fill it. Click on the bush bearing of the crankshaft, choose Up to, and select the piston pin. Repeat the same for the other piston. Everything looks perfect. I'll press Escape, and now we're ready for the analysis. Next, we need to prepare the geometry for defining joints between the connecting rods, crankshaft, and pistons. To do this, we'll add imprints to the coupled components. Navigate to the Prepare tab and click on Imprint tool. As you can see, 8 curves have been automatically selected. Click on the green check mark to confirm. Everything is now set up correctly. I'll press Escape and hide the connecting rods, and you can clearly see the imprints on the cylinder pins and the crankshaft. I'll unhide the rods, and we can now close SpaceClaim. To prepare the model, I'll double-click on the Model cell. Now we're in ANSYS Mechanical. If I expand Geometry and click on each part, you can see that the stiffness behavior is set to rigid because all components are defined as rigid bodies. Also, we don't need to assign any material properties because the geometry is rigid and not flexible in this analysis. Let's move on to the connections. I'll expand the Connections and then Contacts folders. As you can see, there are 4 contact regions automatically created between parts. We don't need these because we'll define joints to connect the components instead. I'll select all the contact regions, right-click, choose Delete, and click Yes to confirm. Now let's start defining the joints between the components. Right-click on Contacts, go to Insert, and select Joint. Since it's difficult to pick the contact regions directly, I'll go to the Display tab and use the Explode tool to slightly separate the components. This makes selection much easier. Let's begin with the first piston. I'll select the interface region between the piston pin and the connecting rod bearing and apply it as the reference scope. Then I'll select the bush bearing of the connecting rod and assign it as mobile scope. By default, the joint type is fixed, but we need to change it to revolute so the connecting rod can rotate around the z-axis. RZ turns blue because bearing is free to rotate around the z-axis. Next, let's define another joint for the connecting rod and crankshaft. Right-click on Contacts, choose Joint, select the bearing of the connecting rod and apply it as reference. It's better to reduce the geometry explode before selecting the crankshaft journal, so you can select it more easily. Now select the crankshaft journal and set it as Mobile. Change the joint type from Fixed to Revolute. Let's repeat this process for the second piston. Right-click on Contacts, choose Joint, and select the piston pin as the reference scope. Then select the connecting rod bushing and assign it as Mobile. Again, change the type to Revolute, allowing the connecting rod to rotate around the z-axis. We'll define one more joint between the connecting rod and crankshaft on this side. Right-click on Contacts, select Joint, choose the bearing as reference and the crankshaft as Mobile. Then set the type to Revolute. Everything looks correct, but the contact names are still showing as fixed, even though the joint types have been changed. Let's rename them properly.
Right-click on Contacts and select Rename based on definition. Now, as you can see, all joint names have been updated to revolute. Next, we need to allow the pistons to move freely along their local z-axis. I'll right-click on Contacts, select Joint, and change the type from fixed to cylindrical. Next, I'll select the piston body and change the connection type from body to body to ground. Finally, I'll set it as mobile. Now the piston can both translate along the z direction and rotate around the z-axis. Let's apply the same setup for the second piston. Right-click on Contacts, select Joint, set the connection type to body to ground, and change the joint type to cylindrical. Finally, click on the outer body of the piston and apply it as mobile. Now let's move on to the crankshaft. The crankshaft rotates around the z-axis, so we need to assign a joint for it. Right-click on Contacts and select Joint. Change the type from fixed to revolute and also change the connection type to body to ground. Then select the outer periphery or cross-section of the crankshaft. The selection won't affect the simulation results, and set it as the mobile scope. Now the crankshaft is able to rotate around the local z-axis. Next, let's rename all joint labels to reflect their correct definitions. Right-click on Contacts and choose Rename based on definition. As you can see, all joint names have now been updated correctly. We can also modify the degrees of freedom of the piston so it only moves along the z-axis. This can be easily done by changing the joint type from cylindrical to general and then adjusting the degree of freedom settings. For example, we can allow motion only along the z direction while restricting all others. After that, right-click on Contacts again and select Rename based on definition. As you can see, now the piston moves only along the z direction. I'll switch the joint type back to cylindrical and rename the joints once more for clarity. Since this is a rigid body analysis without any deformable parts, meshing is not required. If I right-click on Mesh and select Generate Mesh, you'll notice that no mesh is created, which is expected. Now that all connections are defined, let's add an actuator for the crankshaft. We need to apply this actuator at the joint previously defined for the crankshaft. Right-click on Transient, open the Insert menu, and select Joint Load. Now we need to assign the crankshaft joint as the target for the joint load. In the Joint drop-down menu, choose the Revolute Ground joint. Under Type, you can specify rotation, rotational velocity, moment, or rotational acceleration. For this tutorial, I'll select velocity. Next, we can define the magnitude of this motion using tabular data. Before entering the values, let's change the unit from radians per second to RPM. Go to the Home tab, find the Unit section, and change radians per second to RPM. In this example, I'll enter 1000 RPM as the rotational speed. The initial velocity is set to 0, so I'll correct that. Next, let's open the analysis settings. Here, we can change the step end time, which is 1 second by default. I'll leave the default time step options unchanged. Note that the system name appears as transient in ANSYS Mechanical, but in Workbench it is labeled Rigid Dynamics, so don't get confused. Everything looks good. I'll right-click on Transient and select Solve. The solution is complete. It only takes about 2.5 seconds. Now I'd like to visualize the motion of the engine. Right-click on Solution, open the Insert menu, and select Total Deformation. Press F5 to evaluate the results. As you can see, the crankshaft rotates and drives both pistons. To make the motion smoother, we can increase the frame count to 100 and play the animation again. This model is quite simple, but how can we verify the correctness of the joints in more complex assemblies? We need to check the redundancy of the joints. Right-click on Connections and select Redundancy Analysis. Then click Analyze to review the degrees of freedom of each joint. As you can see, this mechanism currently has 1 degree of freedom. However, these 2 revolute joints have redundant fixed degrees of freedom, which should be free. Let's identify which joints they are. Right-click on one of the revolute joints and select Go to Corresponding Joint. We can see that it corresponds to the connecting rod bearing and crankshaft journal joint. The Z displacement and X rotation of this joint are redundant because the connecting rod bushing is already fixed to the piston pin in the Z direction and X rotation. In complex or flexible models, such redundant constraints may cause errors or solver divergence. To fix this, click on Convert Redundant to Free, then click Set to apply the changes. As you can see, the revolute joint changes to a general joint, and now the Z direction and X rotation are free. Let's check the connections again. Select Connections, then go to the Worksheet tab and click Generate. Now the mechanism has 3 degrees of freedom, since the connecting rod crankshaft joint is free in the Z direction. Let's solve the model again. The solution completes successfully. It's better to reset the explode view and check the deformation again. As you can see, there's no noticeable difference in the motion between the 2 joint configurations. Now I want to define acceleration, constant speed, and deceleration phases for the engine. I'll go to the Analysis settings and set the number of steps to 3. Step 1, acceleration from 0 to 1000 RPM. Step 2, constant speed at 1000 RPM. Step 3, deceleration back to 0 RPM.
We can also change the current step. For example, we can switch to Step 2 or Step 3. I'll set the step end time to 5 seconds because I want to analyze the mechanism for a total of 5 seconds. Then I'll go back to Step 2 and change the end time to 3 seconds, so the engine runs for 2 seconds at a constant RPM.
I'll set Step 1 to end at 1 second, Step 2 to end at 3 seconds, and Step 3 to end at 5 seconds. Now I'll go to the joint load settings and specify the rotational speed. I'll set it to 0 RPM at 5 seconds and 1000 RPM at 1 second and 3 seconds. So the engine accelerates from 0 to 1 second, runs steadily from 1 to 3 seconds, and decelerates from 3 to 5 seconds. Now we can solve the model. I'll right-click on Transient and select Solve. The solution is complete. Next, I'll click on Total Deformation and play the animation. As you can see, the mechanism works perfectly. The tabular data shows the maximum, minimum, and average deformation with respect to time up to 5 seconds. I'd like to make the animation smoother, so I'll increase the frame rate to 100 and play it again. Now I'll extend the total time from 2 seconds to 10 seconds and replay the animation. You can clearly observe that the crankshaft rotation speed increases at the beginning and slows down at the end of the motion. That concludes this tutorial. If you found it helpful, please like the video and subscribe to my channel for more ANSYS tutorials.